Swayam Prabha. Digital India. Educated India.
Now we are going to discuss the Unit 4. The topic is linear regression and dimensionality reduction with principal component analysis and machine learning problems. And these are all the following topics to be covered in the Unit 4, and these are all the lesson plan regarding that linear regression and problem formulation. It comes under the linear regression. Next, parameter estimation under the topic of parameter, and Bayesian linear regression under topic of Bayesian, maximum likelihood as orthogonal projection, dimensionality reduction with the principal component analysis and problem setting, maximum variance perspective, projection perspective of eigenvector computation. Next, low rank approximation of a PCA in high dimension, key steps of PCA in practice, latent variable perspectives, central machine learning problems, data, models and learning, and empirical risk minimization, parameter estimation, and probabilistic modeling and inference, and directed graphical models, solving problem by searching by problem solving agents, and example problem searching for solution, uniformed search strategies, and then informed heuristic search strategies, then heuristic function and problem discussion. These are all the topic to be covered. And before going to linear regression, we have to discuss the data, model and learning. And when model and meet data, the first part of the lectures, we introduce the mathematics that form the foundation of many machine learning methods. The hope is that a reader would be able to learn the rudimentary forms of the language of mathematics from the first part, and we will now use the describe and discuss machine learning. The second part of the lecture introduce 4 pillars of machine learning. They are regression and dimensionality reduction, density estimation and classification. The main part of the lecture is to illustrate how the mathematical concept introduced in the first part of the lecture can be used to design the machine learning algorithm, and that can be used to solve the tasks within the remit of 4 pillars. And we do not intend to introduce advanced machine learning concept, but instead to provide a set of practical methods that allow the reader to lecture the knowledge they gain from the first part of the lectures. It also provides a gateway to the wider machine learning literature for readers already familiar with the mathematics. So, it is worth at this point to pause and consider the problem that a machine learning algorithm is designed to solve. As discussed in the chapters, there are 3 major components of the machine learning system. One is data, another is model, third one is learning. So, the main question of the machine learning is, what do we mean by good models? The word model has many subtitles, and we will revisit it multiple times in this chapter. It is also not entirely obvious how to objectively define the word good. So, one of the guiding principles of machine learning is that good models should perform well on unseen data. So, this requires us to define some performance metrics such as accuracy or distance from ground truth, as well as figuring out ways to do well under these performance matrices. So, this chapter covers a few necessary bits and pieces of mathematical and statistical language that are commonly used in the following data. So, the table 1 8.1 example data from a fictitious human resource database that is not in the numerical format. So, name given directly Aditya, Bob, Choli and Diosuk and Elizabeth, and corresponding gender is given, degree is given, postcode is given, age is given, annual salary is given. Now, use this talk about the machine learning models. By doing so, we briefly outline the current best practices for training models, such as resulting predictor does well on data that we have not seen. So, data as a vector. We assume that our data can be read by the computer and represented adequately in the numerical format. So, data is assumed to be tabular in the table as well as figure 8.1, where we think of each row of the table as representing particular instance or example, and each column to be a particular feature. In recent years, machine learning has been applied to many types of data that do not obviously come into tabular numerical format. For example, genomic sequences, text and image contents of web page and social media graphs. So, we do not discuss the important and challenges aspects of identifying the good features. Many of these aspects depend on domain expertise and require careful engineering, and in recent years they have put under the umbrella of data science and reference, Stay, Adhikari and Dionero. Even when we have a data in tabular format, there are still choices to be made to obtain the numerical representation. For example, the table 8.1 gender column categorical variable may be converted into numbers 0 representing male, 1 representing female. Alternatively, the gender could be represented the numbers -1, +1 respectively as shown in the table 8.2. So, this is the 8.2 table, the data from fictitious human resource database and converted to numerical format. So, the gender represent -1, +1 and corresponding degree also mentioned in the corresponding the numbers, and with the help of the latitude and longitude of the degrees also mentioned. So, like that you have to conversion is most important. Furthermore, it is often important to use the domain knowledge when constructing the representation, such as knowing that university degree progress from bachelor to master to PhD, or realizing that the postcode provided is not just a string of characters, but actually encodes an area in London. In table source that we converted to data from table 8.1 to a numerical format, and each postcard is represented as 2 numbers. So, even numerical data that could potentially be directed read into a machine learning algorithm should be carefully considered for units, scaling and constraints. So, without additional information, one should shift and scale all columns of the dataset such that they have an empirical mean of 0 and empirical variance of 1. So, for the purpose of this lecture, we assume that the domain expert already converted data appropriately. So, each input xn is a d-dimensional vector of real numbers, which is called features, attributes or covariates. So, we consider a data to be of the form as illustrated in the table 8.2. Observe that we have dropped the name column of the table 8.1 in the new numerical representation. There are 2 main reasons why this is desirable. Number 1, we do not expect the identifier to be informative for the machine learning task, and we may wish to anonymize the data to help protect the privacy of the employees. So, in this part of lecture we will use n to denote the number of examples in the data set and index the example with a lowercase n equal to 1 to n. We assume that we are given a set of numerical data represented as in the array of vectors, and each row is a particular individual xn, often referred to as an example or data point in the machine learning. So, the subscript n refers to the fact that this is nth example out of the total n example in the data set. So, each column represents a particular feature of interest about the example, and we index the feature as d equal to 1 to d, and recall the data is represented as a vectors, which means that each example, each data is a d-dimensional vector. So, the orientation of the table originates from the database community, but for some machine learning algorithm it is more convenient to represent example as a column vectors. So, let us consider the problem of predicting annual salary from age based on the data in the table 8.2. This is called it as supervised learning problem, where we have a label yn as the salary associated with the example xn as the age. So, the label yn has various other names including target, response variable and annotation. So, the data set is written as the example of label pairs x1 y1, x2 y2 and so on xn yn. So, the table of example x1 to xn is often concatenated and written as x in r power n cross d, and the figure 8.21 illustrates the data set consists of two rightmost columns of the table 8.2 where x equal to age and y equal to salary. So, figure 8.1 is a toy data of the linear regression training data in xn yn, pairs from the rightmost two columns of table 8.2. We are interested in the salary of the person, aged salary x equal to 60, illustrated as a vertical dashed red line, which is not the part of the training data. That is the meaning of the picture, variable x to y of the linear regression. And we use the concept to introduce the first part of the lecture to formalize the machine learning problem, such as that in the previous paragraph represent the data as a vectors and allow us to use the concept from linear algebra already introduced in many machine learning algorithm. So, we need to additionally be able to compare two vectors, as we will see in the chapter. Computing the similarity or distance between the two example allow us to formalize the intuition that example with similar features should have the similar labels. So, the comparison of two vectors requires that we construct a geometry and allow us to optimize the resulting learning problem using the techniques from this chapter. So, since we have a vector representation of data, so we can manipulate data to find a potential better representation of it. So, we will discuss finding good representation in two ways. One is finding lower dimensional approximation of the original feature vector, and another one is using nonlinear higher dimensional combination of the original feature vector. So, in this chapter we will see an example of finding a low dimensional approximation of original data space by finding the principal components, and finding the principal components closely related to concept of eigenvalue and a singular value decomposition already we introduced. For the high dimensional representation, we will see an explicit feature map of phi of dot that allow us to represent inputs xn using a higher dimensional representation phi of xn. So, the main motivation for higher dimensional representation is that we can construct a new feature as nonlinear combination of original features, which in turn may make the learning problem easier. So, we will discuss the feature map and show how this feature map leads to kernel in this section. In recent year, deep learning methods have shown promise in using the data itself to learn new good features and have been very successful in areas such as computer vision, speech recognition and neural language processing. So, we are omitting the fuzzy ideas, only these areas we are covering. And the example of the function, the black solid diagonals and its prediction at x equal to 60, that is f of 60 equal to 100 will come. So, this is the mathematical description of the back propagation, a key concept for training the neural network.